we both work in new fab. So today we are going to talk about expansion of plasma cleaner capabilities. In new fab, we have, let me hide this floating control. Okay, in new fab, we have various etch processes like wet chemical etching for silicon dioxide, RIE for silicon and oxides of nitrides, some polymers, then deep RIE to make deep trenches in silicon, which is basically a Bosch process, xenon fluoride etcher for silicon. Then we have oxygen plasma cleaner, which currently being used for etching photoresist and polymer. So why plasma etching? Like it gives a clean and reproducible process, compatible with automation. Basically, it is anisotropic etching, which allows us to transfer nanoscale features precisely. And this doesn't affect the bulk material. It's only near surface process. So basically, the plasma is the fourth state of matter, which is basically all species, ions, and electrons coexist in the plasma. Typical electron densities are 10 power 9 to 13 per cubic centimeter. And the temperature of electron is around like 10,000 Kelvin, which is basically comparable to the photosphere of the sun. So it has electrons, ions, radicals. Ions, the difference between ions and radicals is ions are like charged. They have a number of electrons is not equal to the number of protons, and their number of electrons are even number. Whereas radicals are not charged particles, they have no charge. Their number of electrons are equal to number of protons, and they have one unpaired electron in their valence shell, and their number of electrons are odd. But radicals are very reactive, and ions and radicals are the key components in this etching process. Generally, number of radicals are more because ionization, like to break the covalent band, the energy required for that is less than the ionization energy. How do we form plasma? There are two ways. In one configuration, basically, we have a parallel plate capacitor configuration. We apply the RF field, then RF field accelerates the electrons. So electrons gain energy, which is basically a combined effect of oscillating RF electric field acceleration and the elastic scattering of the electrons with neutral atoms and the field lines. That gives, when the energy is sufficient enough, like more than the first ionization threshold, then it will ionize the ions, giving more electrons. And these more electrons again participate into this process, giving an avalanche of electrons. That's how the plasma comes into existence. So we call this configuration as a capacitively coupled plasma. It is a low density plasma, electron densities are 10 power 9. Then in second configuration, we magnetically induce magnetically coupled plasma, where you have RF coil, which gives the magnetic field in a vertical direction. And again, the electrons are accelerated by RF field, and those. But in the coupled plasma, the resulting ions and electrons interact with the fluctuating magnetic field here to generate enough energy to ionize more atoms by collision. So this type of configuration is called inductively coupled plasma because of the magnetic induction. And generally, it leads to high density plasma. Electron densities are like 10 power 13. This allows us to control independently energy and the ion flux. And also it improves selectivity and etch rates. Third slide. Plasma chemistry, just an example, like if you dissociate CF4 atom molecule, it gives you CF3 and fluorine radicals. If you ionize argon, it gives you argon ion. Then if you take an example of silicon etching, it takes 4 fluorine radicals and forms the silicon SiF4 gas, which is pumped out. So this is how you etch silicon. So for silicon, there are oxides and nitrides. We generally, mostly the fluorine chemistry is used here. For metals, mostly chlorine chemistry used. Of course, you can use fluorine too. Organic solids can be easily removed by oxygen and CF4. For gallium arsenide, 3,5 semiconductors, and even the chromium, mostly chlorine-based chemistry. And these are the etch products formed in that process. There are some materials which are difficult to etch, cobalt, gold, silver, nickel, iron, all these, because they do not form the volatile halides. Copper can be etched because it has one halide, which is volatile at about 200 degrees Celsius. Okay, so reactive etching is an isotropic process, which etches in all directions in an equal amount with high selectivity. For example, is etching silicon with a radical fluorine. Ion etching is an anisotropic etching, which has a lower selectivity and etch rate. Example is etching silicon with argon ions. However, reactive ion etching is an isotropic process, which has a better selectivity and much higher etch rates. Okay, so current capability of plasma cleaner. Here, it can be used in a plasma etching or RI mode. You can precisely clean optical components or silicon molds. It can be used for photoresist ashing. Ashing is basically a removal of photoresist, and also you can do DISCOM, basically removal of residual photoresist. You can remove organic contaminants by chemical or physical sputtering. You can plasma treat surfaces to introduce polar functional groups like carboxyl, carbonyl, and hydroxyl. This induces the high surface wettability and also improves the adhesion. So that's why most of the photoresist is spread evenly on a plasma treated wafers. It can be used for to sterilize microbial contaminants. So here we have our top touchscreen interface with a RF power of like 300 watt, operated at like 13.56 megahertz. And you can independently control all the functions of this, either in a manual and automatic mode. We use only one gas currently, which is oxygen. Some plasma processes, just an example, like oxygen removes organic contaminants by chemical reaction, which is reactive oxygen radicals, and sputtering like energetic ion, oxygen ions. If you use argon plasma, then it's basically both ion bombardment and sputtering. Argon does not react with the surfaces. So for argon and oxygen combination, surfaces can be cleaned with the combination of sputtering and chemical reaction. And plasma treatment, you can apply it to the wide variety of materials as well as complex surface geometries without affecting the bulk properties of the material. So you can clean AFM cantilevers, glass semiconductors, pattern PDMS, EM grids, gold surfaces for self-assembly experiments, some polymers, carbon nanotubes, quartz crystals, optics and crystals for spectroscopic measurement, even nanoparticles treated with the, you can control the size and the shape of the nanoparticles with a plasma treatment. You can also achieve nitrogen doping of graphene. to incorporate nitrogen into a graphene structure to alter its electronic properties. We have few etch modes here, reactive ion etching mode, where sample is placed on a power electrode and ions induced by RF power directly attack the substrate and thereby increasing the etch rate. In plasma etching mode, samples are placed on a grounded electrode. Ions do not attack directly here, but radicals react with the surface, giving you the etching. So this configuration, there is a less plasma damage. Downstream mode, you can put a perforated grounded electrode between the sample and the electrode here. That further minimizes the plasma damage. So accordingly, if the sample is placed on the shelf, that gives you RI mode. If the sample is placed at the bottom, which is the plasma etching mode. We have few recipes Sarkan has created. Basically, the photoresist stripping, discom, surface treatment, chamber cleaning. These are just an example recipes, but in addition to that, people can make their own recipes in that. Surface treatment with plasma. If you see silicon wafer before and after treatment, the water droplet weightability of the surface has drastically enhanced with the plasma treatment. You can see from the contact angle. Similarly, for PMMA, again, the weightability is enhanced after the plasma treatment. So you can either make it hydrophilic or hydrophobic, it depends. Plasma cleaning of a silicon mold for nano implant. Recently, we had a user, he wanted to clean a silicon mold. He fabricated using this basic lithography and etching process. Silicon mold was treated with trichlorosilane to create a hydrophobic surface. And we wanted to reduce, clean the PDMS residues and the trichlorosilane. If you see the SM image, that gap was like 200 nanometer, and he could not remove it any other technique. So with the plasma treatment, we successfully removed that. RI Samco, we have that, and basically it has a fluorine-based chemistry for several things: silicon dioxides, nitrides, polymers. You can also use argon and plasma. Oxygen plasmas in there. Basically, it's the same similar parallel electrode configuration, giving you an anisotropic etching. Several gases are used, but this is one of the highly occupied instruments, and people are also doing polyimide etch there, so it gets contaminated. So that's why expanding capability of a plasma cleaner will allow additional recipes. And we can take some load off of this RI system. And we know that photoresist removal can be significantly enhanced by just the addition of CF4, small amount to oxygen, also nitrogen to oxygen, also CF4 to nitrogen. So, and also we can remove the hardened photoresist, which is by basically an ion implantation. So here I will stop and I will let Sarkan speak about the second part about the expansion of this plasma cleaner capability. Okay, Sarkan, it's over to you.
Okay, so I'm gonna switch to my screen now.
Oh, I should stop it, right?
It should be fine.
Oh, okay.
So I'm just going to talk about the technical aspects of the what's coming to the plasma cleaner. So it will be not as deep. So we are adding these three gases. So we currently only have oxygen and we will have CF4 and nitrogen and argon. The CF4 and nitrogen is expected to increase the etch rate and improve the selectivity a little bit with when it comes to polymers. A lot of our users are using our plasma etchers uh, to pattern polyamide films, and the polyamide is the captain material. It's relatively harder to pattern, but with these two additions of CF4 and nitrogen, we can achieve a lot. I mean, with CF4, we will gain a little bit of etch rate. So instead of if you get one unit of etch rate with oxygen, you'll get 1.20, so like 25% more increase with CF4, and with nitrogen it's even greater. But with what's nice about nitrogen is we're expecting 3 times more selectivity. So your masks can be thinner, and it will be easier to pattern, and you can achieve more complex geometry is a lot more easier with this recipe, hopefully. And as just Anil was talking about, we would like to take the load off, some of the load off from the RIE Samco, and this will greatly help with that. Also, we have the argon addition with this expansion. I mean, it's not going to be. I mean, argon etching is usually slow compared to chemically etching with radicals. It's more of like a physical etching, like sputtering. You just accelerate argon ions, and just they hit the surface and remove the material, break off some material. But it will help us to achieve kind of to etch some metals. For example, if you want to create thin masks of chromium or titanium, we're expecting to we will be able to do that with this edition. So we found some papers from the past. We dig out some like old vacuum science papers, and people have shown, like with polyamide or other polymers, with the addition of nitrogen on the right hand side, you can see, or CF4, you can achieve increase in the etch rate, and you can also presume some selectivity, or in case of nitrogen, you can increase it to a certain extent, actually. I mean, the etch rate you'll see in these figures are not going to correspond to our machine, because each chamber is different. So we'll have different etch rates, but the relative increase should be there. And we're going to test everything, once the installation is complete. We'll have nice and solid figures, and we can advise our users on what to use on which type of polymer they're trying to etch. And so this is our current configuration. We only have one mass flow controller, which is controlled by the microcontroller of the machine, and the screen Anil just showed you. And it controls the chamber and the MFC. That you can choose different flow rates, and the oxygen is only connected to it. So this is how it will look like. So we are anticipating no additional training for our current users, so they can just come and use it. There will be a manifold at the backside of the tool, so you can select which gases you need to use. Unfortunately, they have to be manually operated, but argon and oxygen will flow through the same MFC that we already have. We're going to install another one, which will control the flow of CF4 or nitrogen into the chamber. Yeah, let's see. So, I mean, this is kind of like a technical background. So this is the backside you obviously never see. So we have this support structure of the lab in the chases, right? So we have these all process lines. We design new lines to be mated with the back of the plasma cleaner, so everything will run smoothly, hopefully. All right, and we also get an extra shelf, so which will allow us in two ways. The first one is once we put the second shelf in the ground as a ground electrode, we will improve the electric field distribution inside the chamber, or like over your substrate, so that the uniformity will hopefully be improved, because so normally the ground is the chamber itself, and the shelf is the active electrode. So you have this diverging or converging electric field lines from the walls. And when you have this true parallel plate behavior, we will have more uniform electric field distribution over the substrate, and it will etch a lot more uniformly. And we can also use this the second electrode in powered mode. So we can put this electrode in the lower shelf, lower position, and this one on the upper position, and that way will increase the capacity by 2. So instead of putting 6 wafers in there, you will be able to put 12 wafers in case you need to do a lot more work. So that's the another advantage we're coming. All right, so that's about it for my part. Now, if you have any questions, we're happy to answer.
Serkan, can you show that plot that you had? Can you hear? Hello?
Hello, yeah, I hear you.
Okay, can you show that plot, not this one, the paper that you were showing?
Yeah.
So on the right-hand plot, it shows with the addition of nitrogen, you can go from, okay, that's the selectivity, and etching rate, it goes from what, 2.2
to 3.2 almost
to
3. Yeah.
2.2 to 3.
Yeah.
So that is the percentage increase that you were talking about, 1.3 or something?
Yes, yes.
Okay.
But
Okay.
but at the same time, it also improves the selectivity by 3 times, which is pretty good.
Yeah, and this selectivity is with what?
They measured it with respect to titanium, but in principle, that's what people usually use to pattern polyamides. You put some sort of metal mask on top of it, and so I mean, with any metal, it should be we should get similar numbers.
All right.
Hi, Serkan or Anil. Serkan or Anil, can you hear me?
Yes.
Yeah, sure.
Yes, I have a question about the plasma cleaning for silicon. Do you know exactly how it is cleaning and what it cleans off? We have, I'm using a plasma cleaner to clean silicon wafers in our own lab, but the plasma doesn't look like it's pure oxygen. And so I was wondering if that's an issue when it comes to cleaning.
Which plasma cleaner are you using?
We're using one in our own lab. I was wondering if it was worth it to use one with a better vacuum so that the gas in the chamber is more pure oxygen.
I see. And is the plasma created with the same technique, or it's a different?
Oh yeah, same technique.
Same technique. It could be oxygen purity could be a problem, but you can try with this plasma cleaner in your fab, and let's see what improvements you can get. Basically, you can clean organic contaminants of the surface of silicon, or if you have any residual things there from the prior process that can be cleaned. So you can try and see, compare it. Once we compare it, we can exactly identify what was going on in your plasma cleaner, right?
Do you know if the organics require oxygen plasma?
Yes.
Okay. All right. Thank
Basically,
you.
because you want radicals to remove organic contamination, because basically it will form, it has to form some functional group on top of the surface, which is like water molecules or CO2, which will be pumped out. So that's how you clean your organic contaminants. So you need oxygen.
I see. All right. Thank you.
Yeah. Of course, you can knock them off with argon also, but then you will have little damage to your surface. Not much. Any more questions?
Say a little more about the same question. It depends what kind of mode you are using in your own plasma cleaner, you know. So Sarkan has showed many modes that are possible with our plasma cleaner. So it's an RIE mode, and then it is a plasma mode. So we have capability to increase etching even if it is not vacuum issue in there.
Yeah.
So is your plasma cleaner has this flat parallel plate configuration, or it has a barrel type configuration?
I believe it has a flat parallel plate configuration.
So you have something like this?
Yeah, yeah.
Okay. And separation is same?
Oh, sorry, what's up?
Separation?
Separation, I don't know the distance.
And
Yeah, you
are
can.
you using plasma mode, or you are using the RIE mode? That could be.
Yeah, I think it only, I mean, it doesn't have a way to select between the different modes. And I know that the oxygen plasma is present because we've used it to etch graphene before.
Mm-hmm.
The issue is that the plasma color appears more like purplish, and I know oxygen plasma tends to be more of like a blue hue, I think. So I was wondering if that was like how effectively it was cleaning the silicon wafer.
Purplish, oh, that's interesting.
Yeah.
Hmm.
And the purplish color usually comes from like you have air or some nitrogen and
nitrogen, yeah, most likely.
Yeah. So you have some problem with your, I think, contamination in your oxygen.
Yeah.
The chamber is leaky.
Yeah. The vacuum on the vacuum for the chamber is not that great, and we don't pump down for that long either. So I think that's the biggest issue. But I mean, if it's effective enough in cleaning, I guess it doesn't matter too much. I was just wondering if you guys knew, like, how pure of the oxygen plasma do I need in order to get effective cleaning?
I mean, I can, according to this paper, anyway, at least I can share that. It's, you see, when you have more oxygen, more nitrogen in your oxygen, it reduces the etch rate, and the selectivity is going bad too. So it's you just need the right combination of nitrogen in there, not more, not less. So
Right.
yeah, that's kind of like an evidence that if you have purple plasma, you have a lot of nitrogen in there.
Mm-hmm.
Yeah.
I see. All right. Thank you.
Well, if there are any more questions, we can answer those. Otherwise, that was great. Thank you, everyone.
Yeah. Thank you.
Well, thank you everybody for joining.
Yeah.
And look out for our next Tech Talk next month.
Okay.
All right.
Thank you.
Okay. Thank you, everybody.
All right.
Okay. Bye.